Honors Chemistry Section 14.2 lesson video. And I personally love gas laws so much. I mean, it really rivals stoichiometry for me. I love it that much. But anyway, so when I was student teaching many years ago, I had some students that had trouble remembering the gas laws. So I wrote this to help you remember them. Now when I first read it to you, it's going to make no sense. But in the next few slides, I'll kind of go through and explain what it means. So it's Boyle is the VIP, Charles likes DirecTV, Gay and Lussac will TP, the house directly next to me. So thank goodness DirecTV actually is something, otherwise this wouldn't make any sense. And then for the few of you who don't know what TP means, it's when you go toilet paper a house, when you roll a house. So we're going to break it down one line at a time and I'll explain to you what it means as we go. So the first line is Boyle is the VIP. Well, Boyle's law states that for a given mass of gas at constant temperature, the volume of the gas varies inversely or indirectly with the pressure. And so what I did was I color-coded everything. So Boyle is the VIP. V is volume. It varies inversely, that's where our I comes from, with pressure, and that's where our P comes from. So if you know Boyle is the VIP, you know Boyle's law states that volume and pressure are indirectly related. So what does indirectly or inversely proportional mean? That means if volume goes down, then pressure goes up. Because as we squeeze a gas into a smaller container, the pressure is going to increase because there will be more collisions. So there is a formula, it's P1 times V1 equals P2 times V2, where our pressures are our P's and our volumes are our V's. The ones just mean the initial pressure and volume, and our twos mean our final. So what's going to happen is we'll have an original volume and pressure. And so see here we have now increased the volume, so we might need to calculate the new pressure because now the pressure should be lower. So let's look at what a question looks like. So what I like to do is label my information in the question because eventually this list is going to be very long of different formulas, and so you got to be able to pick which one to use. So it says a balloon contains 30 liters, so that is the first volume that I see, of helium gas at 103 kPa. Well, that's the first pressure that I see, so I'm going to call that P1. What is the volume? So that means, okay, well, I must be looking for V2, because I already have the volume here, of helium when the balloon rises to an altitude where pressure is only 125 kPa. So there's my P2. So I can look at my question and see I have a V1, a P1, a V2, and a P2. So that's how I know I'm using this formula. I know right now it's obvious, but that's because we haven't learned the other ones yet. Alright, so I know that P1 V1 equals P2 V2. I am solving for V2. See, it asks me what is the volume. So to get P2 on the other side, I divide. So V2 is P1 times V1 over P2. And then since I already labeled everything, I just plug it in and it's super easy. So my P1 is 103 kPa. My V1 is 30 liters. And my P2 is 25 kPa. Now, as far as units go, you can plug in any unit for pressure, kPa, ATM, millimeters of mercury, torr, anything. But if you have two of them, they have to be the same unit. Okay, so when we start the gas laws problems, I'm not going to make you do any converting just so you can get used to using the formulas. But you'll find that as I go through the PowerPoint, we'll start converting more. Okay, and then volume, again, it can be milliliters, it can be liters, as long as if there's two of them, it's the same. Or if it had specifically asked me what is the volume in milliliters or liters, then I would need to make sure my answer is in that unit. So, as always, I just multiply the top two numbers and divide by the bottom, and so for this one, I ended up getting 123.6 liters. Sorry, I was trying to make sure I was on the right question. So 123.6 liters because those kilopascals cancel and I'm left with liters. And so there's my answer. And that's all you have to do. Okay, so let's look at a couple more. If you're feeling confident, go ahead and pause the video and try the next one. Otherwise, we'll look at it together. Okay, so if you want to try this one, go ahead. Otherwise, we'll look at it together and you can try the bottom one. So it says the pressure on 2.5 liters. Y'all, even though it starts with the word the pressure, this is not the pressure. It says the pressure on 2.5 liters. So this is a volume. Like, you've got to get used to the fact that volume is liters, milliliters. It could be centimeters cubed, meters cubed. Those are all units of volume. So the pressure on 2.5 liters of N2O changes from 105 kPa. So there's my first pressure. And so again, y'all, for pressure, you're looking for units like kPa, ATM, millimeters of mercury, torr. So 105 kPa to 450 kPa. So there's my second pressure. If the temperature does not change, what will the new volume be? So I'm looking for V2. All right, so again, my pressures are the same unit, so I don't need to convert anything. So let's go ahead and set up our formula. So P1V1 equals P2V2. I'm solving for V2, so to get P2 on the other side, I just divide. Now y'all, if you're having algebra problems, like on how to rearrange a formula, that would be something you would need to ask me outside of class time. I don't have time to teach you algebra in class, but I'll be glad to help you outside of class on that. All right, so P1 is our 105 kPa. V1 is 2.5 liters. And P2 is 40.5 kPa. So if you look, my kPa cancel. I'm left with liters, so I multiply my top two numbers and divide by the bottom. And so for this, I get 6.48 liters. Just like that. So hopefully if you tried that one on your own, you got it right. If you didn't though, pause it and try this one. And now we'll look at it together. So it says a gas with a volume of 4 liters, so there's my V1, at a pressure of 205 kPa, so there's my P1, is allowed to expand to a volume of 12 liters. So there's my V2. And again, volume doesn't have to be in liters, but they just have to be the same. And so it is, liters and liters. What is the pressure? So I'm looking for P2 in the container if the temperature remains constant. Okay, so this time I'm looking for pressure. It didn't specify what unit, so I'm just going to keep the original unit that they gave me in the question. All right, so I got to rearrange my formula. So P1V1 equals P2V2. This time we're solving for P2, so the way we get V2 on the other side is just divide. So P2 is P1V1 over V2. And then once you've labeled everything in the question, it's super easy to just plug it in. So my P1 is 205 kPa. My V1 is 4 liters, and my V2 is 12 liters. So those liters cancel, and so see this time I'm left with kilopascals, which is fine, I'm looking for pressure. And so when I multiply the top and divide the bottom, I get 68.3, and my unit is kilopascals. So again, I didn't need to convert because they didn't specify a different unit of pressure. Now if they had said what is the pressure in torr, then I would have had to take my kilopascals and then I would have had to convert it to torr at the end. All right, so hopefully you got that one right. So let's move on. So that is Boyle's law. So remember, Boyle is the VIP, so volume is indirectly related to pressure. All right, so next is Charles. So the next line of my saying is Charles likes direct TV. Well, Charles' law states that the volume of a fixed mass of gas is directly proportional to its Kelvin temperature if the pressure is kept constant. So I said Charles likes direct TV. That means temperature and volume are directly proportional. All right, so temperature and volume are directly proportional. So his equation looks like this. It's V1 over T1 equals V2 over T2. However, some of you struggle with solving for variables if they're in the denominator. So if you're one of those people, you can just cross multiply. So V1 times T2 equals V2 times T1. Since most of y'all favor that form, although I personally like the original form better, because then the ones are on the same side and the twos are on the same side. But most of you prefer the cross multiplied version, so that's what I'll use in class. So what you have to remember though, on the cross multiplied version, the ones and the twos are not together. All right, so the V's are of course volume, and then the T's are temperature, and then the ones are the initial situations or what's the word I'm looking for? Conditions, and 2 are the final conditions. Now, the thing is, though, it's directly proportional to Kelvin temperature. So if you're given Celsius, you need to convert it. So just as a friendly reminder, to get to Kelvin, it's degrees Celsius plus 273. Okay, so if you remember in Boyle's law, I told you that you don't necessarily have to do converting for volume or pressure unless they don't match. Well, for temperature, it has to be in Kelvin, and that'll be the case for all the gas laws that involve temperature. All right, so let's look at one of these together. So it says a balloon inflated in a room at 24 degrees Celsius, so there's my T1, has a volume of 4 liters, so there's my V1. The balloon is then heated to a temperature of 58 degrees Celsius, so there is my T2. What is the new volume? So I'm looking for V2. All right, so volume can be in any unit, so liters is fine, but temperature has to be in Kelvin. So I'm going to take 24 and add 273, and that becomes 297 Kelvin. And then I'm going to do 58 plus 273, and that becomes 331 Kelvin. Okay, so you have to convert Celsius to Kelvin. So now that I've done that, I'm ready to look at my formula. So it's V1 T2 equals V2 T1. I'm solving for V2, so I can divide both sides by T1. Just like that. So V2 is V1 T2 over T1. And then I'm just ready to plug in. And again, y'all, if you label everything, it makes it super easy. Also, if you label everything, you realize we're not using Boyle's law this time because there's no pressure, there's temperature instead. Okay, so again, this list of formulas is going to get longer and longer, so you've got to know when to use what. So my V1 is 4 liters. My T2, and see, this is where you have to be careful. Even though you'll have T2 written on your paper, you'll still pair it up with T1. But it doesn't go with T1. It's V1 times T2, which is 331 Kelvin. And then divide by T1, which is 297 Kelvin. So my Kelvins cancel. I'm left with liters, which is fine. It didn't specify what unit I needed volume to be in. So I multiply my top 2 numbers, divide by the bottom, and so for this I ended up getting 4.46, and my unit is liters. So the 2 most common things I see happen in Charles' law is 1, people forget to change Celsius to Kelvin, and then 2, you flip your temperatures. I don't know why that's such a common thing. I know you want the ones to be together, but they're not together. Okay, this is a direct relationship. Inverse and direct relationships have 2 different outcomes when it comes to doing math. All right. So if you're feeling confident, go ahead and try the second one. Otherwise, I'll do that one and you can try the third one. So it says, if a sample of gas occupies 6.8 liters, so there's my V1, at 325 degrees Celsius, so there's my T1, what will its volume be? So again, I'm looking for V2 at 25 degrees Celsius. There's my T2 if the pressure does not change. Okay, so again, once I see I have V1, T1, V2, T2, I know I'm using Charles' law. But I have to fix my temperatures. Volume is fine in liters, but temperature has to be in Kelvin. So I do 325 plus 273, and that is 598 Kelvin. All right, so we're just going to add 273 both times. And then I do 25 plus 273, and that's 298 Kelvin. So then I'm ready to rearrange my formula. So V1 T2 equals V2 T1. I'm solving for V2 again, so I'm going to divide to get T1 on the other side. So that leaves me with V2 is V1 T2 over T1. And so now, since I already have everybody labeled, I just plug in. So my V1 is 6.8 liters. My T2, so remember y'all, be careful. I know you want to multiply it by T1, but it's times T2. That is 298 Kelvin. And my T1 is 598 Kelvin. So see, my Kelvins cancel. I'm left with liters, which is perfect because it asked me for volume. And so once I multiply the top and divide by the bottom, I end up getting 3.39 liters. So if you tried that one, hopefully you got that right. And if you haven't tried one, make sure you pause it and try this bottom one real quick. All right, so I'm going to assume you've done that. We'll look at it together. So it says exactly 5 liters of air, so there's my V1, at negative 50 degrees Celsius, so there's my T1, is warmed to 100 degrees Celsius, so there's my T2. What is its new volume, so I'm looking for V2, if the pressure remains constant. Now I know I just showed you 3 examples where we solve for V2. You don't always solve for V2, I just happen to pick 3 where you do. You can literally solve for any of the variables. All right, so volume is fine in liters because I don't have any specified unit for that. The temperature has to be in Kelvin. Now be careful, this is a negative 50. All right, so when I add 273, I get 223 for this one. And when I add 273 to 100, of course, I get 373 Kelvin for this one. All right, so once I have all my numbers ready, I'm ready to use my formula. So I'll just show you how to rearrange it one more time. So we're solving for V2, so I divide both sides by T1 to get it to the other side. Remember, whatever you're solving for, you want it to be by itself on one side of the equation. So it's V1 times T2 over T1. And so then I just plug in. So my V1's 5 liters. Remember, it's times T2. So my T2 is 373 Kelvin divided by my T1, which is 223 Kelvin. So my kelvins cancel. I'm left with liters, which makes sense. I'm solving for volume. So I multiply my top 2 numbers and divide by the bottom, and I get 8.36 liters. And that's it. So hopefully you got that one right. So like I said, y'all, for Charles' Law, you've got to remember to change the temperature to Kelvin if you're not already given Kelvin. Now be careful. Every now and then I give you Kelvin, and then some of you try to change it anyway. Okay, I'm trying to be nice and save you a step. So temperature must be in Kelvin, and then don't get your temperatures mixed up because you're trying to multiply the ones by each other. That only happens in an inverse relationship. This is a direct relationship. Alright, so last part of my little saying is Gay and Lussac will TP the house directly next to me. So Gay-Lussac's law states that the pressure of a gas is directly proportional to the Kelvin temperature if the volume remains constant. So it says Gay and Lussac will TP the house directly next to me. TP stand for temperature and pressure, and since the house is directly next to me, they are directly related. So see, Boyle is the VIP, Charles likes DirecTV, Gay and Lussac will TP the house directly next to me. So hopefully you find that as awesome as I found it when I first made that up. So what does directly mean? It means if temperature goes up, then pressure also goes up. Alright, and so it has a formula similar to Charles' Law, but instead of having volumes on top, it's pressures. So again, if you struggle with solving for a variable in the denominator, you can just cross multiply. So P1 times T2 equals P2 times T1, just like that. Alright, and then that gets everything in the numerator. So we have P1 T2 equals P2 T1. Now again, temperature has to be in Kelvin. That's for all the gas laws. We don't want negative temperature because then we could get a negative pressure. And since Kelvin can't be negative because the lowest temperature possible on Kelvin is 0, then we don't have to worry about getting a negative pressure or a negative volume. Alright, and then of course your P's are your pressure, your T's are your temperature, and the 1's are the initial conditions, and the 2's are the final. So hopefully at this point you're getting good at plugging into a formula, because that's pretty much all this section is. I personally love plugging into formulas, so that's why I love it so much. So the gas in an aerosol can is at a pressure of 103 kPa, so there's my P1, at 25 degrees Celsius, so there's my T1. If the can is thrown into a fire, what will the pressure be? So I'm looking for P2 when the temperature reaches 928 degrees Celsius. So there's my T2. Okay, now again, pressure, the unit's fine. I don't have to have a specific unit of pressure for gas laws. However, I do have to have Kelvin. So I need to add 273 to both of these. So this, of course, will become 298 Kelvin. So 25 plus 273. And then this one over here, when we add 273, is going to become 1,201 Kelvin. Okay, so again, once I label everything, that's how I know which formula I'm using, because I can see I have P's and T's, and so that points me to Gay-Lussac's law. All right, so we have P1 T2 equals P2, T1. We are solving for P2, so I'm going to move T1 to the other side by dividing both sides. So P2 is P1 T2 over T1. And so again, since I have everything nice and labeled, I just plug it in. So my P1 is 103 kPa. And the similar thing happens in Charles' law. It's P1 times T2. So my T2 is 1201 Kelvin. And so see, again, y'all, if you'll label everything in the problem, then it's easier to not accidentally get them mixed up. And then my T1, of course, is 298 Kelvin. So my kelvins cancel. I'm left with kPa, which is perfect. I'm solving for pressure. It didn't specify what unit it wanted, so I'm going to leave it kPa. I multiply my top two numbers and divide by the bottom, and so I get 415.11 kPa. So this right here shows the exact reason you don't want to throw an aerosol can into the fire. Look how high that pressure is. Normal atmospheric pressure is 101.3. So we are at over 4 times normal atmospheric pressure, which is why then the can could explode. All right, so just a little safety hint there. So let's move on and look at a couple more. And so again, if you're feeling confident, go ahead and try the next one. Otherwise, you can watch me do it and you can try this bottom one. All right, so it says the gas pressure in an aerosol can is 1.5 atm. So there's my P1 at 25 degrees Celsius. So here's my T1. Assuming the gas inside obeys the ideal gas equation, that just means it's following the laws that we have, like Boyle's law, Charles' law, all that. What would the pressure be, so there's my P2 that I'm looking for, if the can were heated to 450 degrees Celsius? So there's my T2. Gosh, what is it with us trying to heat up aerosol cans? I mean, when they explode, it is cool, but it's dangerous also. All right, so let's look at this one. So I labeled all my P's and T's. My pressure is in atm, which is fine, but my temperature is in Celsius, which is not. So I need to go through and add 273. So 25 degrees Celsius becomes 298 Kelvin when I add 273. And my 450 becomes 723 Kelvin when I add 273. So then I'm ready to use my formula. So P1 T2 equals P2 T1. We are solving for P2 again. Again, you're not always going to solve for P2. That's just a common thing to solve for. So I divide both sides by T1 to get it to the other side. So P2 is P1 T2 over T1. And so now I'm ready to plug in. So my P1 is 1.5 atm. My T2, remember it's P1 times T2, is 723 Kelvin. And my T1 is 298 Kelvin. So my kelvins cancel. I'm left with atm, which is fine. It didn't specify what unit it wanted pressure in. So I multiply the top and divide the bottom, and I end up getting 3.64 atm. So yet another explanation of why you don't heat an aerosol can. Okay, normal atmospheric pressure is 1 atm. So if you heat the aerosol can, it builds up really fast, and so again, it can explode. All right, so if you haven't tried one on your own, maybe pause it, look at this last one on your own, and then we'll look at it together. All right, so I'll assume you've done that at this point. So it says a large natural gas storage tank is arranged so that the pressure is maintained at 2.2 atm. On a cold day in December, when the temperature is negative 15 degrees Celsius, the volume of the gas in the tank is 3.25 times 10 to the third meters cubed. What is the volume of the same quantity of gas on a warm July day when the temperature is 31 degrees Celsius? All right, so this one is a little tricky, so just make sure you read it carefully before you try it. So pause the video, try it. I'll assume you've done that. Let's look at it together and see if I tricked you on this one. All right, so it says a large natural gas storage tank is arranged so that the pressure is maintained at 2.2 atm. That means there is no P1 and P2. The pressure stays 2.2 atm the whole time, so I don't need pressure on this one. Okay, this is just extra information to me. On a cold day in December, when the temperature is negative 15 degrees Celsius, so there's a T1, the volume of the gas in the tank is 3.25 times 10 to the 3 meters meters cubed. So there's my V1. And y'all, don't let the fact that it's all of a sudden meters cubed throw you off. That's a unit for volume. It says, what is the volume? So I'm looking for V2 of the same quantity of gas on a warm July day when the temperature is 31 degrees Celsius. So there's my T2. So on this one, y'all, hopefully you caught on, this isn't even a Gay-Lussac problem. All right, we don't have pressure. We have volume and temperature. That means this is actually a Charles law problem. So hopefully you caught that on your own. Okay, what throws people off is that extra information right there. You try to use that. If something remains constant, we're not interested in it for Boyle's, Charles, Gay-Lussac's law. Okay, so now that I know this, my volume, that's fine. I don't have to have a specific unit for volume, but my temperatures do need to be in Kelvin. So I take my negative 15 and add 273, and I get 258 Kelvin. And then my other my other temperature, which is 31, becomes 304 Kelvin. All right, so now I'm ready to plug in, and now I know I'm using Charles' law this time because pressure does not change. Okay, so see, that's why I say it's so important for you to label what's in the problem. Because on a test, I'm not going to have a section called Boyle's law, Charles' law, Gay-Lussac's law. They're all going to be mixed together. So you have to be able to read the information from the problem and figure out which formula you're using. All right, so we're solving for V2. So I need to move T1 to the other side, so I divide both sides by T1. So V2 is, I hope y'all can see this low, V1 times T2 over T1. And so then I'm just ready to plug in. So my V1 is 3.25 times 10 to the 3 meters cubed. Remember, it's V1 times T2. So my T2 is 304 Kelvin. And then I divide by my T1, which is 258 Kelvin. So my kelvins cancel, and at this time my unit for volume is going to be meters cubed. Okay, remember, it's whatever the other unit for volume is, and it didn't specify that I need to change the units, so I'm going to leave it as that. So I multiply my top two numbers and divide by the bottom, and then I end up getting 3,829.5 meters cubed. All right, so the main thing to be careful of on these three gas laws is make sure you remember that temperature has to be in Kelvin, and then especially when you're using Charles and Gay-Lussac's law, you got to make sure to realize that the ones and the twos are no longer together like they are in Boyle's law. That's a common mistake. But otherwise, hopefully you're finding gas laws as fun as I find them, because I love gas laws.